In this video, we'll be talking about mathematical induction, which is the last topic in our unit on mathematical proof. You might remember inductive versus deductive, uh, those terms from your geometry class a long time ago. And if you remember, deductive reasoning is based on logic and the following of logical steps. It can't be refuted. Inductive reasoning is reasoning based on observation of a pattern, and it's less rigorous than deductive. But mathematical induction is kind of a misnomer in that it isn't. It is a deductive sort of reasoning, but it's a pattern. It comes from a pattern, and you'll see the steps that we use to sort of enforce that pattern is happening throughout the system that we're looking at, throughout the set of natural numbers in this case. So when you see the words mathematical induction, it is actually a deductive process, but it's based on what we see as a pattern, and that's why it's called mathematical induction. So our targets are to form a conjecture for a relationship or pattern based on a set of data, and also to prove a conjecture, the conjectures that we come up with, to be true using this process of mathematical induction. In this video, we're going to be focusing on the second target. We will do some activities together where we look at patterns and try to form conjectures as well. So let's jump right into the definition of mathematical induction. Let n, m, and k be natural numbers such that k is greater than or equal to m. Now k in particular is an arbitrary natural number, and what we do is we say that if a proposition, now proposition just means a statement that we are looking to prove or asserting is true. If a proposition P of n is true for n equals m, and P of k plus 1 is true whenever P of k is true, then P of n is true for all n is greater than or equal to m. An obvious statement. This gets actually a little bit unwieldy when you read it. It sounds kind of foreign, kind of strange, doesn't make much sense. But when you see the process at work, it does make sense, and it's pretty clear. All that we're saying here is that if you know that a statement is true for a certain starting value, and you know that if a statement is true for any arbitrary value, that implies that it will be true for the next value, then that proposition or statement must be true for all values greater than your starting value. You might want to stop that and play that again. You'll see it in the problems that we do together. But here are the steps. We want to show that the proposition is true for some starting value. Now often we start with n equals 1, but that's not necessarily, doesn't have to be the starting value. But we want to show that the proposition in question is true for a starting value, in this case n equals 1. That is to say, P of 1 is true. The second step is the one that gives people a hard time, at least conceptually. We want to assume that the proposition in question is true for some arbitrary value k. We're not proving it. We're assuming it. Now generally that would be a bad thing to do. Right? We can't assume that something's true. We don't know that it's true. And we don't. But we're going to assume that the proposition is true for some value k. That is, P of k is true. Now, we don't know that P of k is true, but we are assuming that it is, for the purposes of step 3. To show that if P of k is true, then the next P of the next value must also be true. P of k plus 1 must be true. What we mean here is that P of k implies P of k plus 1. It's like a domino effect. If a proposition is true for one value, then it must be true for the next value. But if it's true for that next value, then it must be true for the value following that, because k is arbitrary. K can be any natural number that we want. What we're trying to show is that if the proposition is true for some arbitrary value, then it must be true for the value following that. And that's why we make this assumption step, to facilitate proving this third step. Once we've proven this third step, and we know that the proposition is true for some starting value, well then the proposition must be true for the value after the starting value. Because what we've said is if p of some number is true, then the next value, p of the next value, must also be true. So if I know p of 1 is true, and I've proven that if p of k is true, then p of k plus 1 is true, then those two things together imply that when n is 2, p of 2 must be true as well. But if p of 2 is true, then p of 3 must be true. And if p of 3 is true, p of 4 must be true, and so on. So let's look at exercise 1. Again, if this doesn't quite make sense, it will as we go along. Prove that the sum of the first n natural numbers is equal to the expression n times the quantity n plus 1 all over 2. This is a familiar expression to you. Undoubtedly, someone has told you the story of Gauss and how he was able to sum the first 100 integers very quickly by writing them forward and then writing them backward and then adding the columns, and each of the columns added up to 101. And he realized that he had twice as much as he wanted, so he, he found this formula and was able to astound his teacher by doing this. And so we're going to prove this in a different way using mathematical induction. So what's the proposition in this case? The proposition is that the sum of the first n natural numbers is equal to n times the quantity n plus 1 over 2. That's our proposition. So our first step in mathematical induction process is to show that this is true for the first natural number, p of 1. We want to show that p of 1 is true. Well, that's pretty trivial. The sum of the first one number is 1, right? So, and when we put 1 into our formula here, we get 1 times the quantity 1 plus 1 over 2. Of course, that equals 1, and so p of 1 is true. Now, generally speaking, this first step in mathematical induction is very simple, almost trivial most times, to show that it's true for the base case. We're basically just plugging in 1 to our proposition and verifying that that proposition works. Secondly, we're going to assume that our proposition is true for some value k, and k is arbitrary, but it's a member of the naturals. So we're assuming that 1 plus 2 plus 3 all the way up to k, that sum will be k times the quantity k plus 1 over 2. Again, we've not proven this. We're assuming that it's true. Now, given that step 2 is true, we're going to show that p of k plus 1 must also be true. And we do that using the expression we've just assumed to be true. So let's start. We'll write that we need to show that 1 plus 2 plus 3 all the way up to k plus 1. So we've added all of the natural numbers up to k plus 1. We need to show that that's equal to the expression that our proposition is talking about with k plus 1 substituted in for n instead of k, right? So we've got k plus 1 in for this n, k plus 1 in here, all over 2. Notice the question mark over this equal sign. We haven't proven this to be true, and so I'm denoting that by inserting that question mark over the equal sign to say this is what we're trying to prove. We don't know that it's true. We're going to do some algebra and simplifications to see if we can get these two expressions to be equal to each other. And it's important to note also at this instance that when you're trying to prove that two expressions are equal to each other, you want to work on one side of the equation, not on both sides. And so we're going to stick to one side of the equation and get it to match the other side. It's maybe something of a subtle point, but if you're working on both sides of the equation, you don't end up actually proving what you're asserting. You prove something that's related that may or may not really be enough of a proof of what you're looking for. So it's important to always work on one side of the equation, and I will hold you accountable for that. So how can we get one side to look like the other side? We're going to work here on the left-hand side, and what we want to do is use the assumption step that we've assumed here in step 2 to help us prove that step 3 would be true as well. And so I look at my assumption step and I see that on the left hand side here I've got the sum of 1 through k. I have an expression for that. It's k times k plus 1 over 2. But I've got that same sum right here in the current line. So I can do a substitution for that expression in for this sum. And so we've got k times k plus 1 over 2 plus k plus 1 equals what we've said before. And again, we don't know that it's true, so we have the question mark over the equal sign. Now it's a matter of simplifying the left-hand side some more and trying to get the expressions to match. So we'll get a common denominator, multiplying top and bottom of the second term by 2, combining those fractions, and then realizing that k plus 2 is simply k plus 1, and we see that indeed these two expressions are the same. Right? Now, have we proven that p of k plus 1 is true? No. We've proven that if p of k is true, p of k plus 1 will be true. So this by itself, steps 2 and 3 by themselves, haven't proven anything. They've shown a relationship, an implication, that if p of k is true, if p of some number is true, then p of the next number will also be true. However, when you combine that with the first step, where we've shown that the proposition is actually true for a certain number, these combined tell us that since p of 1 is true, p of 2 must be true. We're simply substituting 1 in for our k. We don't have to assume that p of 1 is true. We've proven it. But because p of 1 is true, p of 1 plus 1 is true. And so p of 2 is true. But because p of 2 is true, p of 2 plus 1 is true. And so p of 3 is true. And so we've shown that if p of any arbitrary value k is true, then p of k plus 1 must also be true. And those three steps combined yield a result that has a domino effect where the proposition being true for each number implies that the proposition is true for the next number forever. And so we've proven that the conjecture is true for all n in the natural numbers.